Pulse width modulation is a term that we use to describe a specific type of digital signal. This example here is a pulse width modulated digital signal that varies the voltage between 0 volts and 3.3 volts. Varying the voltage between 0 volts and 3.3 volts, or between low and high, allows us to be able to duplicate the results of an analog signal that is used to send a varied amount of voltage to an LED. Decreasing the amount of voltage that we send to the LED would then decrease its brightness. If we vary the digital signal over time and we change the amount of time that the signal is going to a high position compared to a low position, we'll be able to duplicate those results and dim an LED with a digital signal. We're going to talk about pulse width modulation and how we use a digital signal to control the brightness of this LED. Go ahead and set up your LED similar to what we set up in Lab 2. You should have your ground in pin number 20. And your yellow wire should be connected to physical pin number 12, GPIO pin 18. After setting up the pins in the appropriate location, we are going to go into the terminal and turn on the LED for the testing that we're going to perform. We need to run the LED on script in order to demonstrate what's happening in this lab. So let's navigate to our folder. And we want to go into Lab 2.0. And we want to run the script 2.1.0 LED on. Your LED should be on now. The script actually ends, and if you recall that we didn't do GPIO cleanup, and so it'll leave the LED on. But that's okay, that'll work well for the measurements that we're about to perform. We're going to use a multimeter in order to understand the voltages that we find on our LED. This will help us later when we start talking about pulse width modulation. So grab a multimeter and we're going to make the following measurements. The first measurement that we're going to make is in DC volts. We will be measuring the voltage between pin R and the ground pin. Take the time to measure the source voltage coming out of your Raspberry Pi. Yours may be slightly different than mine. I got 3.114 volts DC. The value that we expect to come out of the Raspberry Pi is 3.3 volts. The difference is insignificant. When we look at our schematic next to the GPIO pinout, we can see that we've connected R to pin 12 and ground to pin 20. In our program, we commanded the Raspberry Pi to turn pin 12 into an output and make that output high. So we have 3.3 volts commanded from pin number 12 to go into our dual color LED. The next measurement that we will be making is we will check the voltage drop across the R1 resistor. In order to perform a voltage drop on the R1 resistor, we will take our red meter lead and connect it to the R1 resistor on the R pin side. The black meter lead will connect to the R1 resistor on the LED side. Notice that our voltage drop is 1.211. In order to ensure that we understand what's happening here, let's take a closer look at our schematic. Remember that we were showing at the pin R a source voltage of 3.114. We've just performed a voltage drop on resistor R1. we've shown that the resistor R1 is dropping 1.211 volts. These two values can help us to calculate the amount of voltage that will be left when we get to the LED. If we take 3.114 and subtract 1.211, that gives us 1.903 volts available for the LED. Now there will be a slight variation in the numbers that you measure, and there will also be a slight variation in this calculation. There could be voltage drop based on heat or resistance that we're not measuring, but approximately 1.9 volts will be available at the LED. Our final measurement with the multimeter is to check the voltage drop of the LED. In order to measure the voltage drop that is occurring at the LED, we will connect our multimeter red lead on the right side of resistor 1. The red lead will be between resistor 1 and the LED. Our black meter lead will connect to the ground pin. Our measurement is 1.906. Yours might be slightly different. Notice that it's very close to the calculated value that we expected to drop across the LED. The small difference from our calculations isn't that significant. Looking at the schematic again, we remember that 3.114 volts was the source voltage. The voltage drop at R1 was 1.211 volts, and our LED is dropping 1.906 volts. The reason that we perform this exercise is to determine how we will decrease or dim the LED. One of the methods that we might use in order to dim the LED is to increase the resistance of R1. A variable resistor could be installed in place of R1's fixed resistor, and the resistance could be increased or decreased. If the resistance at R1 was increased, we would see a larger number of voltage drop at R1. If R1 had a larger voltage drop, that would mean that at the LED there was less voltage available. This occurs because the source voltage is fixed at 3.114. This particular method to dim the LED is an analog method. We are making small changes to R1, which in turn reduce the amount of voltage that is available at the LED. We will now explore a method to dim the LED using a digital signal from our Raspberry Pi. Since our board has a fixed resistor and not a variable resistor, we'll return to our original values that we measured. The only thing that we can change is the source voltage. The resistance value of R1 and the resistance of the LED are fixed. If we decrease the source voltage by half, we would be left with 1.557 volts available at pin R. That would also decrease the voltage at R1. The voltage drop would be 1.057, and decrease the voltage drop at the LED, which would be 0.953 volts. This would dim the LED. In order to determine or figure out how we decrease the voltage at the source, we need to take a look at the digital signal that we will create from the Raspberry Pi in order to do this. This is an example of a digital signal that we might produce on our Raspberry Pi at physical pin number 12. The digital signal is represented in red, and the blue lines are increments of time. On the bottom part of the axis, the x-axis, we have three different labels, 0, 1, and 2. The 1 and 2 represent seconds in time. So at 1 second, we can see that the digital signal decreases to 0 volts. In between 0 and 1, there are 9 divisions. Those divisions represent tenths of a second. Notice that the line halfway between 0 and 1 is slightly larger. That represents a half a second. At 1/2 second, the digital signal moves from a 0 volts to a 3.3 volts, or from an off state to an on state. On this particular digital signal, the time between 0 and 0.5 is off time. The time from 0.5 to 1 is on time. If we combine the off time with the on time, that signal occurs in 1 second. That 1 second time frame is known as a cycle. We can measure cycles in hertz. 1 hertz equals 1 cycle per second. The on and off time of this digital signal is also referred to as the frequency. The frequency is in reference to this 1 cycle per second. Hertz is a way of measuring the frequency or occurrences of an event over time. Later we will look at how changes in frequency affect our LED. For now, we'll keep this digital signal at a 1 hertz frequency. The next term that we want to define is the duty cycle. The duty cycle represents the amount of time that the signal is high, or the percentage of on time in 1 cycle. In our specific example right here, we see that the off time is half the time, and the on time is half the time. This signal would be defined with a duty cycle of 50%. In order to ensure that we have a good understanding of what the duty cycle of a digital signal is, let's take a look at 2 other examples. We've already defined the top example of having a 50% duty cycle. 50% of the cycle, the signal is in the on position. The next digital signal below that has a 25% duty cycle. 25% of the time, the signal is in the on position. The bottom duty cycle is 75. 75% of the cycle, the signal is in the on position. A circuit that remains on for the entire cycle is said to have a 100% duty cycle. A digital signal that has 100% duty cycle would result in a voltage that stays at 3.3 volts, or whatever the source voltage is. At a 50% duty cycle, that same digital circuit that has a 3.3 volt source voltage would reduce to 1.65 volts over time. Half of the time the circuit is on, and half of the time the circuit is off. A further reduction in voltage will occur at the 25% duty cycle. At 25% duty cycle, the voltage value that we would read is 0.825 volts. At a 75% duty cycle, we will see a change in value from 3.3 volts to 2.48 volts. An important thing to note about duty cycle is we're not really changing the source voltage to 1.65 volts. What's happening is that we are changing back and forth between 0 and 3.3 volts. That change back and forth can happen fairly rapidly, that most multimeters would only register the average that happens over the cycle. So in this case, we'll see the multimeter would go to a 0 value and a 3.3 value within a 1 second time frame and may only then average that at a 1.65 volts. If we were to connect our LED to a circuit that had a 50% duty cycle and the frequency was 1 Hertz, meaning that 1 cycle happened per second, we would likely see the LED blinking. Half the time the LED would be off and half the time the LED would be on. That half a second we would be able to pick up with our eyes. The multimeter may also see that variation or change. To decrease the ability of our eyes to be able to see the blinking, we need to increase the cycles per second. The chart on the left shows an example. If we were to just increase the cycles per second to 2, that would allow us to have the LED off for only a quarter of a second. Then it would be on for a quarter of a second, off for a quarter of a second, and then on for a quarter of a second. So my duty cycle still remains 50%. 50% of the cycle, which in this case is a half a second, the LED is off. And then 50% of the cycle, the LED is on. But now I'm running 2 cycles per second instead of 1 cycle per second. Now you probably would still be able to see the LED at 2 Hertz blinking. We would really need to increase it to something more like 100 Hertz. The duty cycle would remain the same, it's just that the number of cycles per second would increase. In our next lab we will use an LED and a digital signal with pulse width modulation to demonstrate both duty cycle and frequency changes and how they affect the LED.